The big formula for a 4x4 determinant has 4 factorial, that's 24 terms, and each term is a product of 4 numbers with a plus or minus sign. A 5x5 determinant, that's 5 factorial or 120 terms. There has to be a better way, and there is. Peel off one row, and the 4x4 problem becomes 4 3x3 problems. Each of those 3x3 problems becomes 3 2x2 problems, and a 2x2 determinant you can do in your head. That cascade of breaking things down is called cofactor expansion. Start with the 2x2 matrix with entries A, B, C, D. The determinant is A times D minus B times C. Now let's reframe this formula as a cofactor expansion along row 1. Entry A sits at position 1, 1. Delete row 1 and column 1. The remaining submatrix is just a single entry D. The checkerboard sign is -1 to the power 1 plus 1, which equals +1. Next, entry B sits at position 1, 2. Delete row 1 and column 2, and the remaining submatrix is just C. The sign here is -1 to the power 1 plus 2, which equals -1. Now assemble the terms. A times +D plus B times -C. And that gives us AD minus BC, the same familiar formula. But from a new perspective, using cofactor expansion, let's do a quick numerical check. Take the matrix with entries 3, 7, 2, 5. The first term is 3 times 5, which equals 15. The second term is 7 times -2, which equals -14. So the determinant is 15 minus 14, which equals 1. Time for some precise vocabulary. The minor Mij is the determinant of the submatrix that remains after you delete row I and column j from the original matrix. The cofactor Cij attaches a checkerboard sign to that minor. Cij equals -1 raised to the power I plus j multiplied by the minor Mij. Let's see the sign pattern for a 5x5 matrix. At position 1, 1, I plus j equals 2, which is even, so the sign is plus. At position 1, 2, I plus j equals 3, which is odd, so the sign is minus. Continuing across row 1, the signs go plus, minus, plus, minus, plus. Row 2 flips minus, plus, minus, plus, minus. Row 3 goes back to plus, minus, plus, minus, plus. And this alternation continues down through rows 4 and 5, just like a chessboard. For example, at position 2, 3, I plus j equals 5, which is odd, so the sign is minus. The rule is simple. When I plus j is even, the sign is plus. When I plus j is odd, the sign is minus. And the top left corner is always plus. Now let's write out the general cofactor expansion formula along row I. The determinant of A equals A sub I 1 times C sub I1 plus A sub I2 times C sub I2, and continuing this pattern all the way through A sub In times C sub In. In other words, we take each entry in the chosen row, multiply it by its corresponding cofactor, and then sum up all those products. This is the key idea. Each entry pairs with its cofactor, and this formula works for any row I that you choose. Furthermore, since the determinant of A equals the determinant of A transpose, cofactor expansion along any column works just as well. So you have complete freedom to expand along whichever row or column you prefer. Let's compute a 3x3 determinant. Matrix A has row 1, 2, 0, 1, row 2, 3, 5, 2, row 3, 1, 4, 7. We'll expand along row 1. The first entry is 2 at position 1, 1. We delete row 1 and column 1. The remaining 2x2 submatrix has entries 5, 2, 4, 7. The checkerboard sign at position 1, 1 is plus. That 2x2 determinant is 5 times 7 minus 2 times 4, which equals 35 minus 8, which equals 27. So the contribution from this term is 2 times 27, which equals 54. The second entry is 0 at position 1, 2. 0 times any cofactor is 0, so we can skip this term entirely. The third entry is 1 at position 1, 3. we delete row 1 and columns 3. The remaining submatrix has entries 3, 5, 1, 4. The checkerboard sign at position 1, 3 is plus. That determinant is 3 times 4 minus 5 times 1, which equals 12 minus 5, which equals 7. So the contribution is 1 times 7, which equals 7. The grand total is 54 plus 0 plus 7, which equals 61. And therefore, the determinant of A is 61. That 0 in row 1 eliminated one entire cofactor computation. This is the practical power of cofactor expansion. Hunt for zeros. Let's compare the two approaches side by side. If we expand along column 1, the entries are 2, 3, and 1. There are no zeros, so all 3 cofactors must be fully computed. That's 3 cofactors worth of work. But if we expand along row 1 instead, the entries are 2, 0, and 1. That 0 in the middle means the entire second term becomes 0 times its cofactor, which is just 0. We can skip it entirely. So we only need to compute 2 cofactors. Both approaches give us the same determinant of 61, but the row 1 expansion saves us real work. The takeaway is important. The determinant comes out the same regardless of which row or column you choose, but your workload changes dramatically. Always scan the matrix first and pick the row or column with the most zeros. This idea scales up beautifully. Consider a 4x4 matrix where column 2 happens to contain 2 0 entries. If we expand along that column, we get 4 terms in the cofactor expansion. But 2 of those terms vanish because the zeros kill their cofactors. Only 2 terms survive, and each one produces a 3x3 submatrix whose determinant we need to evaluate. Now, each of those 3x3 determinants itself breaks down into 3 2x2 problems through further cofactor expansion. Picture this as a tree. At the top, the root node is labeled 4x4 determinant. 4 branches descend from it, 1 for each entry in column 2. But 2 of those branches are pruned. They correspond to the 0 entries and carry a times 0 label, so they contribute nothing. Each of the 2 surviving 3x3 nodes then sprouts 3 branches downward, leading to 2x2 leaf nodes. These leaf nodes glow because they represent direct computations, simple AD minus BC calculations. This reveals the recursive nature of cofactors. An n by n determinant spawns n subproblems, each of size n minus 1. Those subproblems spawn their own subproblems, shrinking all the way down until we reach 2x2 matrices that we can compute directly. Here's a common mistake to watch out for: confusing the checkerboard sign with the entry's own sign. These are separate things. Let's walk through an example carefully. Suppose the entry aᵢ₂ equals -4. We highlight this entry in blue. Now step 1, the position is row 2, column 1. So I plus j equals 2 plus 1, which equals 3. Since 3 is odd, the checkerboard sign is -1 raised to the 3rd power, which gives us -1. We'll mark this as a red badge. Step 2, suppose the minor m21 equals 11. We'll show this in green. Step 3, now we build the cofactor. C21 equals the checkerboard sign times the minor. That's -1 times 11, which equals -11. Notice the sign attaches to the minor first, forming the cofactor. Step 4, the determinant contribution equals the entry times the cofactor. That's -4 times -11, which equals +44. So there are 3 distinct components at play: the entry value shown in blue, the checkerboard sign shown in red, and the minor shown in green. The checkerboard sign multiplies the minor to form the cofactor, then the entry multiplies the cofactor. A common wrong approach is to apply -1 to the I plus j to the entry instead of the minor. The right approach is the sign attaches to the minor first, and then the entry multiplies the resulting cofactor. Keep all 3 components separate in your mind. 3 methods for computing determinants, 3 different trade-offs. Let's compare them side by side. First, the pivot formula. You row reduce the matrix and track the operations along the way. Its complexity is order n cubed, making it the fastest method for numerical computation. Its flavor is algorithmic based on row operations, and its strength is speed. Second, the big formula. This uses all n factorial terms, where each term is a signed product over permutations. Its complexity is order n factorial times n, because each of the n factorial terms involves multiplying n entries together, and this method is explicit, but impractical beyond small n. It's best suited for theoretical proofs or very small matrices. Its flavor is exhaustive, it accounts for all permutations, and its strength is explicitness. Third, the cofactor formula. This is recursive with n factorial worst case complexity, but zeros in the matrix prune branches and reduce the work. It's best for sparse matrices and symbolic work. Its flavor is divide and conquer, and its strength is flexibility. You can expand along any row or column. To summarize, pivots are algorithmic. The big formula is exhaustive. The cofactors are divide and conquer. Each method reveals a different structure, hiding inside the determinant. Cofactor expansion bridges the compact pivot approach and the sprawling big formula. It provides a structured, recursive way to break any determinant into pieces small enough to handle. And that 2x2 formula, AD minus BC, it was cofactor expansion all along. Under this machinery of minus cofactors and the checkerboard of signs is the foundation for important topics you'll encounter later. It leads to Cramer's rule, a method for solving linear systems using determinants. It leads to the classical adjoint, which gives a formula for the inverse of a matrix. And it leads to characteristic polynomials, which you'll meet when studying eigenvalues. So cofactor expansion is not just a computational tool, it's a gateway to deeper ideas in linear algebra.